So, uh, good evening, everyone. Welcome to the last live interaction session for the course Renewable Energy Engineering, Solar, Wind, and Biomass Energy Systems. I hope I am audible, and I request uh, you to mute your mic so that there won't be any disturbances. Yeah, thank you so much. So, let's just wait for a few minutes before we start our session for today. Yes. So I think we can start our session for today. Let me just present my screen. I hope I am audible. Okay. So are you able to see my screen? Yeah. Thank you so much. So yeah, I welcome you all for the last week live interaction session for the course Renewable Energy Engineering, Solar, Wind and Biomass Energy System. Myself Pratyumnan, a PhD scholar at the Indian Institute of Technology, Guwahati Chemical Engineering, is responsible for conducting this live interaction session every week. This course is offered by Professor Vaibhav Vishant Gaut sir and Professor Anandalakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati, under the NPTEL program. So today, as I said, it's the last live interaction session, and we will be trying to conclude of what we have learned throughout the 12 weeks in this course. So today we will have a brief overview and solve some problems on all the three energy system, that is your solar, wind and biomass energy systems. So yes, let's just begin for today. So initially we haven't solved few problems related to wind energy in the last interaction session. Due to some time constraints or time limitations, we were not able to solve all the possible kind of questions, possible model of questions for the wind energy. So today we will start with that and then progress towards solar energy and conclude our session with the biomass energy systems, where we will see how to solve a few problems on each of these concepts. So in wind energy, if you see, we have covered almost all the concepts, starting from how wind energy is a renewable energy resource, how solar energy indirectly contributes for the wind energy, and we also talked about the different type of windmills available, the horizontal axis windmill and the vertical axis windmill, its types, so in the horizontal axis windmill you have the multi-blade and the propeller type, whereas in the vertical axis you have the Darius and Savonius type and their characteristics. So the multi-bladed system, the number of blades and the diameter of the blades of the rotor. Similarly in the propeller type, and then we discussed about the blades having the airfoils. So then we discussed about the different characteristics of the airfoil, such as your chord length, airfoil span, and then we discussed about the drag force, lift force acting on the airfoil, the pitching moment. After that we discussed about solidity parameter, the tip speed ratios, and then we proposed how does the power actually vary with the wind speed. We discussed about the three important type of wind speed. One is the cut-in speed, rated speed and cut-out speed, and their characteristics and their probable speed ranges. After which we discussed about the Betz limit, which is nothing but the maximum theoretical capacity for the wind energy generation, that is nothing but the 59% or 16/27. And then we discussed how Betz actually proposed this, how he compared the rotor of the windmill to an actuator disc model and used the linear momentum theorem to derive the Cp max value as 16/27 or 0.593. So after that we also saw the correlations for the power coefficients, and then we solved some of the problems. So we will continue solving problems today also. So before going to a new problem, in the last class we saw few problems. Over there we actually kind of didn't solve it thoroughly. So, and moreover, for a practice purpose, I think it is necessary for us to solve that problem once again. So let me just move back to week 12 PowerPoint presentation. Yes, this question number 1, if you see. So here what they have asked us, what is the question is, the wind is at a condition of 1 standard atmospheric pressure, the wind is blowing in that particular location, and that location has an atmospheric pressure of 1 atm and 25 degrees Celsius and is flowing at a velocity of 2 meter per second. So they are asking us to calculate the total power of the wind in kilowatt per meter square. So yesterday what happened was that we took the value of rho as 1.293, as one of you among the attendees have used this value. So for practice purpose I took the same value of rho as 1.293, but in as such, if you are not given with the air density data, suppose the air density data is not given to you in the question, then it becomes your responsibility to actually calculate the density of the air, and for that you are actually given with the pressure as well as temperature. So yesterday we saw how to calculate, but we actually didn't calculate. So I think it is better for us to have that practice once, so that it will, it will be comfortable for you if you face this kind of question in the future. So if you see, we assume that the air actually obeys the ideal gas law, and then we have proposed the relationship as PV equal to nRT, so the ideal gas law equation, and from there we have derived that the density is nothing but it's equal to Pm by RT. So we took n is nothing but the number of moles as a ratio of the mass to the molar mass of the air. So when you substitute n as n is equal to mass divided by molar mass in the ideal gas law, you get mRT by capital MB. So we know that mass divided by volume is nothing but density. So then this equation, if you see this equation 2 can be simplified as P is equal to rho times R times T by capital M, and from here we can write the value of rho as Pm by RT. So this is how you arrive at this expression, that is density is nothing but is the product of the pressure times the molecular weight of the air divided by the gas constant times your temperature of that gas. So here we have the pressure as 1 standard atmospheric pressure. So 1 atm, or let me just make another slide and then solve it. So 1 atmospheric pressure is nothing but, when you express it in terms of Pascal, it is 1.01325 times 10 power 5 pascals. So this is 1 atmosphere is 1.01325 into 10 power 5 pascals, and the molecular weight of air you can assume it as 28.84. R is so 28.84 kg per kilomole. The value of R is, the gas constant is 8.314 kilojoule per kilomole Kelvin. And your temperature is given as 25 degrees Celsius. So if you convert to Kelvin, it would be 273 plus 25, that is nothing but 298 Kelvin. So now we will substitute. So density is nothing but it's equal to pressure in Pascal, so 1.01325 into 10 to the power 5 times 28.84 divided by R, that is 8.314 plus 298. So you can calculate the density as, so I hope you are calculating along with me. So the density will be nothing but (29222213). So 0.572. So if you divide, you will get density as, but here if you see, you have to be very cautious with the units. So that is one of the reasons why we are doing this problem. So Pascal can be written as Newton per meter square, right? And your molecular weight is nothing but it is in kg per kilomole, and your R is nothing but kilojoule per kilomole times Kelvin, that and then your temperature is in Kelvin. So this Kelvin and Kelvin will get cancelled because this is divided, or otherwise let me, so this Kelvin at the denominator and this Kelvin will get cancelled, kilomole will get cancelled. You can express kilojoule in terms of kilojoule in terms of Newton, because so kilojoule can be expressed in terms of Newton. So then over here it will, you have, because since it's here it is in kilojoule, so it will be 1000 joule per kilomole Kelvin. Since kilomole will get cancelled, and once you bring down all the units, I mean once you do all that simplification, you will have a additional 1000 in your denominator, and then the units will be in terms of kg per meter cube. So it is very important that as you do work with the numerical side by side, it is also better for you to work with the units, because otherwise, since here it is in kilojoule per kilomole Kelvin, you have to have a 1000 factor extra in your term. Otherwise your density will be in terms of 1000 something. So let's just calculate the density now. So it will be 1.179 kg per meter cube. So if suppose if we have not divided the value with 1000, then the answer would be somewhere around 1179 kg per meter cube, which means that the density of the air is actually going to be greater than the density of the water, and air is very air is in a gas form, right? So that will have a much lower density compared to the water which is in the liquid form. So that will be wrong. So this 1000 factor is very important. So that's the reason I told, when you solve a problem, it's always better to solve the units part side by side along with the numericals part. So once you now have calculated the density, if you go back to this question, then it's just about multiplying. So you know the available power wind, available power in the wind, so that is nothing but half rho a v cube. Now we have calculated the value of rho as 1.179, and since here they have asked us to express the total power in kilowatt per meter square, so you can take the area to the other side. So it's just that now you need to actually change the value of rho. So then if you take this as a density and calculate, then the power available in the wind per unit area is nothing but 0.5 times rho, that is 1.179 times v cube. V is taken here as 2, so that will be 2 cube. So 2 cube will be nothing but 8. So if you calculate, yeah, 1.179 times 0.5 times 8, So this will be your watt per meter square. So the power available in the wind per unit area will be 4.716 watt per meter square. And since they have asked us to express that in kilowatt per meter square, so it's just that you need to divide this by 1000, so it will be 0.004716 kilowatt per meter square. So here this problem I have specifically taken because we need to have a practice of how to calculate the density in case if it is not given in the question. So since here like everything is in atmospheric pressure is 1 atmosphere, temperature is 25 degrees Celsius, the variation of what we did yesterday and today will not be much. But suppose if the condition is not the same, then over there will be a huge difference. So it is always better once to calculate your density and then progress. So if you see in the video lecture over there, Anandalakshmi ma'am took the density value as 28.97. I have taken here as 28.84. So the 28.84 that I took here is actually considering only oxygen and the nitrogen is present in the air. But if you take other contributions also, then you have to take the value of density, take the molecular weight of air as 28.97. So it's better I write here as 28.97. It won't create a much difference in the value, but still it is better to take the density of the air as 28.97 and then solve. Now here we have another one question that we solved yesterday. Here they are asking us to calculate the rotational speed of the rotor, but they have asked us to express that in the units of RPM. So once you calculate the value of omega using the tip speed ratio, so here we use the tip speed ratio yesterday as 4. So we equated 4 is nothing but omega r by u. U is nothing but your wind speed or free stream velocity of the wind. Usually you can take that as a wind speed which is given in the question. So once you substitute the value, you will get omega is nothing but 4 times u by r. R is nothing but the radius of the rotor. So diameter of the rotor was given as 30 meters. So radius is nothing but diameter by 2. So that will be 15 meters, and your u is given as 14 meter per second. So if you multiply 4 times 14 by 15, then you will get 3.773, but the units for this is in radian per second. Now if you want to express the rotational speed or angular velocity in terms of RPM, then we need to further do some calculation. So omega in RPM will be nothing but, or to be honest, number of rotations or rotational speed will be nothing but 2 times pi times omega by 60. So this is how we are supposed to calculate, convert the units from radian per second to rotations per minute. So pi value is 3.14, omega is 3.733 as we calculated yesterday, or now also we calculated, divided by 60. So we are supposed to calculate this 2 into 3.14 times 3.733, the whole divided by 60. Just a second. oh sorry, omega will be equal to 2 pi times the number of rotation times 60. I'm sorry, this is my mistake. So the angular velocity is nothing but it's equal to 2 pi times the number of rotations by 60. So then in that case you have to multiply 3.733 times 60 divided by 2 times 3.14. So if you do that, then the value will be 35.66 rotations per minute or RPM. So this is how you need to calculate. So if they are asking you to express the angular velocity in terms of radians per second, then it's just direct substitution. But if they are asking you to calculate the rotational speed in terms of RPM, then you need to express omega in terms of number of rotations, and then from there you need to calculate the rotational speed in terms of RPM. So after this they just ask for the tip speed. So now here we know that tip speed ratio as 4, and that times your wind velocity, that is 14, will give you omega r. Omega r is nothing but it is the tip speed of the blade. So tip speed ratio is defined as the tip speed of the blade or blade tip speed divided by the free stream velocity of the wind. So that is what is tip speed ratio. So if they are just asking you to calculate the tip speed, then it is nothing but omega r. So tip speed is equal to omega times r. R is the radius of the rotor. So I hope, so these were the two things that yesterday we actually missed. So I hope now it's actually clear. If you have any doubts, then do let me know now, or we can proceed to the next question. So we have a question here. Yesterday we saw the methodology, but we were unable to solve. So today we will solve this question once again. Like, we will solve this question for the first time, but yesterday we saw the method. So I hope now you will be able to remember the, or yes, I hope you will be able to tell me how to solve this problem. So just let me read out the problem and then let's solve this. So they are asking you to consider a wind turbine, and then that turbine is 15 meter in dia. It is actually rotating at a speed 20 meter per second. The velocity of the wind, is rotating at 130 rpm, and the wind velocity is 20 meter per second. Just there is a correction here. Yeah. So there is a wind turbine. It is actually having a diameter of 15 meter. It is rotating at a speed of 130 rpm. The velocity of the wind at that location is 20 meter per second. They have given the conditions for that location as temperature is 35 degrees Celsius, and then the pressure is 1 atmospheric pressure. The power coefficient, that is nothing but it's your Cp value, is given as 0.25. They are asking you to calculate the value of tip speed ratio, torque coefficient, that is Ct, and then the torque available at the rotor shaft. So torque coefficient, as we saw yesterday, it is nothing but it's actually defined as the ratio of the actual torque that is available in at the rotor to the theoretical torque, and they are asking you to calculate the torque available at the rotor shaft. So yesterday we tried solving this problem, so let's just try to solve this problem now. And yeah, so let me just wait for a few minutes, and I hope you will be able to solve this problem now. So first you need to calculate the area, and then once you calculate the area, you need to actually calculate the tip speed ratio. After you calculate the tip speed ratio, you have this relation, that is tip speed ratio is nothing but it is the power coefficient by torque coefficient. So we know power coefficient. Once you calculate the tip speed ratio, you will be able to calculate the torque coefficient. So once you know the value of Ct, then it is nothing but torque available at the rotor shaft is Ct times half rho A u square. So you know u, that is the wind speed, A is nothing but the area of the rotor or of the rotor shaft, and then density you can calculate. So yes, so what will be the answer? It's actually a quite we have made sure that the problem is quite lengthy, so that you actually get the practice also while solving, like calculating the value of omega in radian per second, the density. So this question, once you solve, you will be able, as you keep solving, you will be able to get a practice on those two aspects of the solving also. So yeah, let's just calculate this question like yesterday how we calculated. The model is very similar. So yeah, so first they are asking you to calculate the tip speed ratio. So tip speed ratio is nothing but it is blade tip speed of the blade, tip speed of blade divided by the wind speed. So this is expressed as omega times r divided by u. So omega here we do not have it in radians per second, they have given it as rotations per minute. So we are supposed to convert this. So as I said, omega is nothing but 2 times pi 3.14 times the number of rotations, so that will be 130, the 130 rotations per minute. If you see, the wind turbine is rotating at this speed, so 130 divided by 60. So if you calculate this, then omega is 13.606 radians per second. So now you have the value of omega. R is nothing but the turbine, that rotor of that wind turbine is 15 meter in dia. So dia is diameter. So 15 by 2 will be the radius. So that will be 7.5 meter. And the wind is actually flowing at a velocity of 20 meter per second. So tip speed will be nothing but 13.606 times 7.5 whole divided by 20. So what is the value of tip speed ratio? So 13.606. Yes. Omega is your angular velocity. Yeah, omega. So you want the omega equation like that. So omega will be 2 pi times that rotating speed, which is in RPM, divided by 60. Yeah, okay. Actually, over there also it is over there they have actually given it in rotations per minute, but we are supposed to convert that to radians per second. So that's why we do this extra step. If the value is actually given to you in radians per second, then you can just substitute that value in your tip speed ratio formula. So then it will be 13.606 times 7.5. So 102.045 is nothing but is your tip speed of the blade, that divided by 20, 5.102. So this is your tip speed ratio. So first part of the question is done. Next is nothing but you are supposed to calculate the torque coefficient. So torque coefficient is nothing but power coefficient by tip speed ratio. So that will be power coefficient is 0.25 and tip speed ratio is 5.102. .049. So this is your torque coefficient. Now you know torque coefficient, so you can write the expression for torque as nothing but torque is power coefficient, torque coefficient times the the theoretical torque. So that is half 0.5 or half times rho, that is your density of the air, A times u square right. So here we are supposed to calculate the value of A. A is nothing but it is the area of the rotor. So A will be equal to pi, that is 3.14 times r square. So 7.5 square. Now you are supposed to calculate the density as we calculated few minutes back. So rho is equal to, that is density is equal to Pm by RT. So P is nothing but the pressure. They are telling, or they have given that the pressure is 1 atmospheric pressure. So we have seen that 1 atmospheric pressure is equal to 1.01325 into 10 power 5 pascals. So that we can write here. Times the molecular weight, I am going to take here as 28.97, divided by R, that is your gas constant 8.314 kilojoule per kilomole Kelvin, times your R, T is 35 degrees Celsius. So 273 plus 35 will be 308. 308 Kelvin. And since there is since the R is expressed in kilojoule per kilomole Kelvin, so we we have a 1000 factor extra in the denominator. Let me just scroll back to that slide. Yeah, so if you see here, since it is in kilojoule per kilomole Kelvin, we are supposed to express that kilojoule in terms of joule. So we will have a 1000 additional factor in the denominator. So now we are supposed to calculate the density. So it is 1.01325 times 10 power 5 times 28.97. And the denominator is 8.314 308 times 1000. So if you divide these two, then let me just write 2935 385.25 divided by 25607. So the density is 1.146 kg per meter cube. So this is the density of the air. So now we have all the values in our hand. We have torque coefficient that we calculated as 0.049. We have rho, that is 1.146. We have A, that is 3.14 into 7.5 square. So that will be nothing but 176.625 meter square. So now we have all the values. So we can just substitute torque in the shaft, in the rotor shaft is 0.049 times 0.5 times your density 1.146 times your A, that is 176.625 times your U square. So U is 20, so 20 square, or that I can write it as 400. So that value will be 0.049 times 0.5 times 1.146 times 176.625 times 400. The value is around 1983.640, and torque is nothing but force times length, so that is Newton meter. So this much amount of torque is available in your rotor shaft. So this is how you have to solve this question. First you need to calculate the tip speed ratio. Once you calculate the tip speed ratio, use this relation, and then after you use this relation, you can just get the value of torque as nothing but torque coefficient times half rho A U square. So if you have any doubts, then do let me know now before we progress to the next question. Yeah, torque is nothing but the rotational force. So when the wind is blowing against your when the wind is actually flowing, what happens is it has to it will impart some amount of its kinetic energy, and that energy has to actually rotate the wind. So that rotational force in your rotor is nothing but it's called as a torque. Torque is nothing but it's a rotational force. Yeah. Yeah. Now that's how the expression is. See, over there power it will be u cube, for the torque it is u square, because that force is nothing but the, what do you call, the theoretical force is half rho a u square. Yes. Hello. Yeah, yeah, yeah. Okay, so then can we proceed to the next question? So this is the next question. Here they are asking you to estimate the annual production of a 12-meter diameter horizontal axis wind turbine operating at a standard atmospheric conditions. They have given the density of the air, so we don't need to actually calculate anything here, and they have given the average wind speed as 8 meter per second. They are asking us to calculate the annual energy production. Calculate, you can write annual power production, and they are asking you to assume that the site wind speed probability density is given by the Rayleigh density distribution. So yesterday we discussed about two different type of probability density models, if you see, for calculating for finding out the wind speed. One is the Weibull and another one is the Rayleigh density distribution. So now here they are asking you to assume that the probability density function is a Rayleigh distribution, and then based on that they are asking you to calculate the annual power production, the average machine power for your wind turbine. So this we saw in the last yesterday. So over there we expressed, if you want to see the equation, then yeah, here. So this is the average machine power equation. So PW bar. So when there is a bar, it actually means that it's the average quantity. So that is nothing but it's an integral between 0 to infinity PW PU du. So once you integrate this by assuming this function, when you substitute here and then calculate, you will be able to express the average machine power as P into 2 by 3 d square u cube. So let me just take this equation from here and then use it directly here. Actually the derivation is quite long and and quite complicated, so we don't do that derivation here, but if you see the video lectures over there, the derivation for this has been given, so you are always welcome to go and check that, because it's a quite complicated derivation and it will take time to derive it here. So we limit our like, you know, we just take here the formula as rho PW bar is equal to rho times 2 by 3 d the whole square times u cube. So here rho is the density of the air, so that is 1.225 kg per meter cube. D is nothing but the diameter of your uh, rotor of that wind turbine. So that is 12. U is nothing but the average wind speed. So since we are calculating the average power, so we have to take the average wind, and we are given with the average wind here as 8 meter per second. So you just need to plug in these values into the equation and then calculate what will be the average machine power. Once you calculate the average machine power, you need to calculate scale up that to the annual level. Like this is only for a particular hour, so you need to scale up that scale up that to calculate the annual power production. So let's just solve, because this we didn't solve yesterday, so let me just start solving. But as I said, it's just about having this formula and plugging in the values for the variable. So I hope you will also be able to do. So PW is nothing but rho. So rho is the density, 1.225 times 2 by 3 d the whole square. So 2 divided by 3 times the d. D is the diameter, so that is 12, and this squared times u cube. U is 8. So 8 cube. So PW is nothing but the average machine power. So let me just write this: average wind machine power, or average machine wind power, is nothing but 1.225 times 2 by 3 times 12 the whole square times 8 cube. So let's calculate. So 2 by 3 times 12 is nothing but 8. So 8 square times 8 cube will be 8 power 5. So 8, or let me just calculate, 2 by 3 times 12 this whole square. So 8 square, that is 64, times 8 cube. $512. So if you multiply this, then 1.225 times 64 times 512. So it is 40140.8, and the unit of power is watts. So this is the average machine wind power, or average machine power, or average wind machine power you can call, but this is only for a particular hour. So now you need to actually calculate the annual power production. So this has to be multiplied with a factor, so that we can calculate for annual power production. So let me just, annual power production is nothing but it's equal to PW times 8760. So this 8760 factor is nothing but it's for 1 year. So this is the amount of power that is usually generated for 1 hour. So for that, so this power is for 1 hour. Like that, we need to calculate it for 1 year, because we are given the word annual here. So annual means per year. So we need to multiply your average machine power with the number of hours that is present in 1 year, so that we can calculate the annual power production. So how many hours is there in 1 year? So a year has 365 days. So we assume here it's a non-leap year. This, and each day has 24 hours. So this is 8760 factor. So whenever there is a question on annual power production, you need to calculate whatever the average machine power that you get. Once you calculate that, you are supposed to multiply that with the 8760 factor. So 8760 is nothing but 8760 hours are present in 1 year. So we take 1 year as nothing but 365 days, and each day has 24 hours. So (365 times 24) is nothing but 8760 hours. So that is the reason we have this factor. Now we calculate the annual power production as PW. So this is your PW is 40140.8 watts times 8760. So it's just about multiplying. So you get this much amount of watt hour. So let me just copy this. So this much amount of watt hour is the annual power production. So here what I want to say is, in this question we do not have any kind of condition or any kind of constraints on the turbine. So the turbine has an efficiency of 100%, but usually that is not the case, right? Each type of wind turbine, as I said previously itself, it has many different losses. The BETS limit says it's only up to 59%, but apart from that 59, the maximum theoretical power that you can get from your windmill is 59%, like 59% of the available power or the power available in the wind. So only you can harness 59% from that. So that is what was proposed by BETS, and in that 59% also there will be many losses. So one is basically because of the fact that the wake that is formed is actually rotating, another is the drag, and then another one is due to the tip losses, and apart from that you have other kind of losses contributing from the different components present in the wind turbine, right? So when all these losses gets combined, you will have only, you can actually harness or use only approximately 30 to 35% of the power that is available. Here in this question nothing is given, but if you are given with the efficiency of the turbine, if you have certain efficiency, like let's say that the mechanical efficiency is only, let's say 35%, then you are supposed to multiply that efficiency with the annual power, because that is what you can actually harness. Then in that case, if there is a certain mechanical efficiency or turbine efficiency is given to you in the question, then you are supposed to multiply that with your annual power production value. So this will be the annual power production considering the mechanical efficiency into account. This is without considering any kind of mechanical efficiency, without consideration of mechanical efficiency. And this with the consideration of the mechanical efficiency. So this actually depends upon the question. If the question asks if there is anything related to that efficiency percentage, then you are supposed to multiply whatever the maximum power that you get with that efficiency to calculate your final answer. If there is nothing given to you in the question, then you can just leave it as such. So let's again move. So this will be the last question for the wind energy concepts. So if you have, I hope the last question is clear, but in case if you find anywhere difficulty, then please let me know. Or can, oh, you have raised your hand. So do you have any doubt? Uh, or shall we proceed towards the solving the next question? If you don't have any doubts, then we can actually progress towards the next question. So here in this question we will introduce two different type of correlations that we didn't see previously. So with that correlations we will be able to solve this question. So let me just read out the question first. They are asking you to calculate again the annual energy production, and here they are actually using a propeller type wind turbine, and it has a radius of 45 meters and it's operating at a speed of 40 rpm, that is 400 rotations per minute, and it is placed in a location which has an average wind speed of 36 km per hour. They are asking us to assume that the wind turbine is operating with a 35% efficiency, and there are two different conditions. One is only under wake rotation, and where both the wake rotation as well as drag is present. So here let me just start solving, because you actually require two correlations to solve this question. Let's just go step by step slowly so that you will be able to understand this question. So first, since they have asked us to calculate the value of annual energy production, so annual energy production can also be can be expressed as annual energy production, or let's say the power. Initially we will discuss power as nothing but it can be expressed as Cp times half rho A U cube. That is the power that is available in the wind. I hope you remember how we solved. We actually, it is the kinetic energy of the air molecules that is actually is actually getting converted to the wind energy or wind power. So we take wind power is nothing but the differential of kinetic energy with respect to time. So from there we derive the steps, and then we at the end got the formula for the power that is available in the wind as half rho A U cube. So you can always check for that derivation. It will be there in the week 11 live interaction session, also in the video lecture. So here we take so here we know that power is nothing but Cp times 0.5 times rho times A times U cube. A we can calculate because we have the radius of the wind turbine, the rotor of the wind turbine. Rho, they have asked us to assume the density as 1.225. U is average wind speed, that is given as 36 km per hour. here what we don't know is the value of Cp. So we are supposed to calculate the value of Cp, and from there we can calculate the power. So for calculating the value of Cp, we have two different correlations. So let me just write those correlations. So Cp can be expressed as, so only when the wind turbine is operating under wake rotation, then in that case the value of Cp or power coefficient can be expressed as 16/27 times exponential of minus 0.3538 times lambda or lambda is actually a tip speed. Okay, let me just write here tip speed. Tip speed ratio whole power minus 1.2946. So this is the expression. So when the wind turbine is operating under a wake rotation condition, so initially if you see in case of the the linear momentum theorem, we assumed that that there is actually no rotation of wake. The wake is not rotating. So if the wake is not rotating, then in that point of time you did not have to bother about the losses from there, because there will not be any kind of energy dissipation from a stationary wake. But in case of a wake that is rotating in nature, there will be some sort of energy dissipation. So you have to take into account that energy dissipation while calculating your value of Cp. Now another one is when it is operating under the wake rotation as well as the drag effect. And drag. So when there is a drag also, due to the drag is nothing but it's kind of a force that is acting, the frictional force. So due to that also there will be an energy loss. So you need to account for that also. So in that case the value of Cp will be expressed as 16/27. So this 16/27 is nothing but it's the Betz limit. So you can so please keep it in mind. Exponential minus 0.3538 times tip speed ratio minus 1.2946. So after that exponent it is minus this effect of drag or epsilon value times your tip speed ratio. So this is the correlation if you are taking both the wake rotation and drag into picture, and this is the correlation if you are only taking your wake rotation into account. So based on this you are supposed to calculate the value of Cp. Once you know the value of Cp, just about substitution, and then you multiply that whatever power you get with your wind turbine efficiency, which is given as 0.35, to calculate your annual energy production. So let's just calculate this. So these are the two important correlations that we require for this problem. So you can actually take this correlation. This is also there in the video lecture, so you can always refer to that. There is nothing different from what we are doing here. So first is it is only under wake rotation. So if that is the case, then the correlation will be Cp equal to 16 by 27 times exponential minus 0.3538 tip speed ratio times whole power minus 1.2946. So we just need to now calculate the tip speed ratio. So can you just tell me what is the tip speed ratio? Tip speed ratio is nothing but omega times r divided by u, right? So omega value will be what will be the value of omega? So here it is given 40 rotations per minute. So you are supposed to calculate rotations per minute into radians per second. So what is omega value? So omega is nothing but two pi, the rotational speed is 40 divided by 60, right? So what will be the value of this? 2 times 3.14 times 40 divided by 60, 4.1866 radians per second, sorry. So this is the value of omega. R is nothing but it's the radius of the rotor of your wind turbine. So that is given as 45 meters. So here please be careful, we have the value as radius itself and it is not the dia. So if so, this is the place where you need to be careful. If the radius is given, then you can take the value as it is. If it is diameter, then please convert that into radius while solving the problem. So radius will be 45 meters. U is nothing but the wind speed. Wind speed here is given in terms of kilometer per hour. So all the other terms, if you see, are in terms of meters. So but here it is in terms of kilometer per hour. So here you are supposed to convert kilometer per hour to meter per second. So since I think that might be simple, so you can tell me how much is the speed of wind in meter per second. So 36 kilometer per hour is how many meter per second? Yeah, so your u value will be nothing but 10 meter per second. And what will be the value of tip speed ratio? So that is 4.166 times 45 divided by 10. So what will be the value? How much? Yeah, 18.8397. So this is your tip speed ratio. So let me just So now we have the tip speed ratio. So it's just about substituting in that correlation. So Cp value is nothing but 16 by let me just copy that. And in place of tip speed ratio you can substitute 18.8397 I believe. So if you just substitute, then what will be the value of Cp? So it's 18.8397 to the power minus 1.2496. This times 0.3538 the value we got was 6.2233. So this is the, so we have to calculate this value. So Cp will be nothing but exponential of so just a second. So this entire this thing I actually calculated in my personal calculator that I have here. So since it's quite complex, I mean it's difficult to put it in the virtual calculator. So this exponential of this entire term will be nothing but 0.9921. I hope you also got the same value. So are you guys also getting the same value of this term expression? Oh, okay. So yeah, actually I calculated here using my scientific calculator. The value was around 0.9221. So you can actually check this once you, I mean once you have the scientific calculator with you. So this value will be nothing but 16 by 27 times 0.9921. So that will be nothing but 0.58 79. Now you have the value of Cp. So it's just about calculating this power. So power will be nothing but it's equal to Cp, that is 0.5879 times 0.5 times density we have taken as 1.225 times area is pi r square, so 3.14 into radius is radius is 45 meters, so just substitute 45 into 45, pi r square, 3.14 times 45 times 45 times u cube. U is 10 we have calculated, so 10 cube is 1000. So if you calculate, then the power will be 0.5879 times 0.5 times density is 1.225 times area is 3.14 times 45 times 45 into 1000. So your energy will be yeah. So this will be the amount of power that you will be having. This is the amount of power, this is watts. Now we are supposed to calculate the annual power. So annual power will be nothing but 8760 times this much amount of power. It's not much, it's just 2289.624 kilowatts, you can write it. So if you just multiply, then you will be getting 2289.624 times 8760, then this much amount of kilowatt. But this is if the turbine efficiency is actually going to be 1, but here we have a turbine efficiency of 35%, so then we are supposed to multiply this. So then you can call that as you can call this as the, or you can just multiply here also, but yeah, okay, anyway. So annual power will be nothing but this, you can write it as maximum annual power. This maximum annual power times your turbine efficiency. So turbine efficiency here we have seen is 35%, so 0.35. So just multiply that. So this much amount of watts or kilowatt will be your annual power. So this is for if there is only wake rotation. If you have both wake rotation as well as what do you call the drag in picture, then in that case you need to use this correlations. So let us just use that, and so this correlation will come into picture. Here we have been given with the value of epsilon, so that is nothing but epsilon is given as 0.02. Okay, so epsilon is given as 0.02. Epsilon is nothing but it's the ratio of drag coefficient to the lift coefficient. Ratio of drag coefficient to lift coefficient. So keep this in mind, because we need to know what does each variable actually signifies. So from here you can calculate Cp as nothing but it's just about substitution. So this entire formula. And in place of tip ratio you just substitute as 18.8397, and in place of this epsilon you substitute 0.02. In 8397. So if you do this, let me just do it in my personal calculator, the scientific calculator that I have. So this value will be nothing but 0.3645. So you can always verify and check this once whether the value, whether whatever I have done this calculation is right or wrong. So now same procedure, it's just that you need to vary this value of power. So that will be nothing but, it is 0.3645 times 0.5, that is half, rho 1.225, A that will be 3.14 times 45 r square, so 45 times 45 times u cube, that will be 1000. So if you just multiply this, then 0.3645 times 0.5 times 1.225 times 3.14 times 45 square times 1000. So this much amount of power will be, you will be able to, will be available to you. Then you need to express this in terms of annual power. Maximum annual power will be 8760 times this one, and that many watts. And since here the turbine efficiency is only 35%, so that times this will give you a final power, or the power that you can actually obtain. Annual power obtainable or obtained will be this much amount of power. So that's how you are supposed to calculate. These will be the two correlations that you will use. So yeah, only for this question it's all about knowing how to use the correlations, and then how to use the efficiency percentage in calculation for your energy production, for calculating your annual energy. So with this we will be concluding the wind energy part. If you have doubts related to this wind energy, you can ask me now, because after this we will go for a short or a brief discussion about the solar and biomass energy system. Peak power coefficient will be nothing but the maximum coefficient. Like if you see in the video lectures, there is actually one question which asks you to calculate the peak power coefficient. So that is nothing but the coefficient, the power coefficient at the maximum power. So that is called as a peak power coefficient. Like you can go through that video lecture for week 12, second video lecture. You will get a better clarity. Okay. Like in the sense yeah, that will be at the maximum power. So you are supposed to calculate that we can actually express Cp as actual power that is available in the rotor to the maximum power available in the rotor, right? So that Cp at that maximum power is what is called as a peak power coefficient. equation actually I don't have it right now here, so that's the reason I asked you to like go through that video lecture. Like over there that equation is given. Okay. Oh, okay. Then let me do one thing. Since I don't have that equation with me right now, I'll be uploading this PPT. So over there, I will mention that equation also when I'm uploading. Will it be fine with you? Yeah. Okay. Yeah. Sure. Because that I guess it's a quite big equation, and I don't really like I don't remember that equation right now. So yeah, what I'll do is you know how to access the PPT, right? So like in the NPTEL portal, if you see, you will be having this problem solving session. Over there all these PPTs are uploaded. So when I'm uploading this PPT, I will include that formula also. So that will be I guess helpful for you. Now we have actually completed the wind energy concept, and let's just go very quickly through this solar and biomass energy system, like very not really it's just like for a quick revision or like a brief recap of what we have seen throughout this course. I hope you will be able to remember all these concepts. So first question is about calculating the angle, declination angle on March 21st of a leap year having a latitude of 34.08 degree north. Of course that latitude is not necessary for our calculation here. So do you I hope you will be able to remember the definition as well as the formula on how to calculate the declination angle. So declination angle is nothing but it is represented as delta. So yeah. So delta is nothing but the declination angle. So what declination angle means? The center of the earth and the center of the sun, when those two are connected with each other, when those 2 points are connected using a line, the projection of that line on the equatorial plane is called as declination angle. It is represented as by the formula 23.45 times sine of 360 times 284 plus n divided by 365. So this is the formula for the declination angle. N is nothing but the number of days or the nth day, the nth day of the year. So March 31st is nothing but the value of n for March 31st will be, so January has 31, February, since they have told it's a leap year, it will be 29 plus March 21st, so you have to include that date also, so it will be 21. So the value will be 31 plus 29 makes up 60, 60 plus 21 is 81. The value of n is 81. So now you know the value of n, so you can express delta as, so now you can calculate the value of delta. So delta is nothing but 23.45 times sine of 360, 284 plus 81 divided by 365. So the value of delta will be so 284 plus 81 is 365. So that 365 and this 365 will get cancelled. So you then you will be getting sine of 360, and we know sine of 360 is nothing but it is 0. So the value of delta is 0. So the answer is A. I hope this is just for you to for everybody who is doing this course to remember how did we do these calculations at the very beginning of the course. So this value of delta, declination angle, is 0. So what does it mean? What is that particular date on which this declination angle will be 0? So that is called as the equinox days. So if you remember, we have 4, depending upon the declination angle, whether it is 0 or 23.45, we have 4 different days in our calendar year. 2 are called as the equinox days, and the 2 is called as the solstice. So equinox is happens when the declination angle is 0. So equinox happens, or equinox is when declination angle is 0, and solstice is when declination angle is 23.45 degrees, of course. So during this solstice you have 2 days. So that is what is our next question. So now we know that as the if the declination angle is 0, then it is called as the equinox days, and if the declination angle is 23.45 degrees, it is called as a solstice. So this equinox will happen on 2 days in a calendar year, and this solstice will happen on 2 different days in the calendar year. So our next question is this: which of the following can be the probable date of equinox? So one equinox we know is the 21st March, because we have calculated here that the declination angle will be 0. So what is the next equinox day? And which among the two is the solstice, and what is the characteristic of the solstice? So the next equinox days will be in September 22. So on that day again your declination angle will become 0. And the rest 2 days, that is your 21st June and 21st December, are the solstice. So the 21st June is called as a summer solstice, and 21st December is called winter solstice. So the during the summer solstice, the declination angle will be 23.45 degrees. Declination angle is 23.45 degrees. Similarly, during winter solstice also, the declination angle will be 23.45 degrees. And during the summer solstice, the day length will be more. So the day will be the longest day in that particular calendar year, which will be approximately for 14 hours. If you see the daylight, the sunlight will be there for 14 hours. So this is the longest day in a calendar year. And winter solstice, the day length will be the shortest one. Very small, very less amount of sunshine hours. So that will be only for 7 hours approximately. like within that range. So summer solstice, the day length will be more, the declination angle is 23.45 degrees. Winter solstice, the day length will be short, it will be only for 7 hours. Next is about, so that is more about what you need to actually have in mind is about the declination angle concept. So once you have that in mind, then these questions are just about knowing the facts. Now these are more towards logical ones. So in a non-concentrating collector, only beam radiation is used, whether it is true or false. So these are actually, most of these are similar to what you have solved in the assignment also, and this question I guess it's from the assignment. In non-concentrating collector, only beam radiation is used, whether that is true or false. So what do you think? Yeah, I mean, can you explain the reason why it is false? So in case of the non-concentrating collector, what happens is you do not have a collector system that is present. So when you don't have a collector system, then what happens is all the radiation will actually fall onto your collector. So that includes both the beam radiation as well as the diffusive radiation. In case of the concentrating collectors, if you see, you have a collector, a concentrators. So that concentrator will help in concentrating the solar radiation. So over there, in case of the concentrated collectors, it is only the beam radiation that will be used up for the energy storage purpose. Whereas in case of the non-concentrating collectors, since you don't have a concentrators that is available in the system, the entire global radiation, that is your sum of beam plus diffusive radiation, will participate in the energy storage process. Next one is, again it's a true or false. It's about the collector efficiency factor, whether it depends upon the thermal conductivity of the plate. So collector efficiency factor, the definition is nothing but it's the actual useful heat transfer gain rate per tube per unit length to the useful heat gain that would have been possible if the absorber was at a local temperature Tf. So if you remember in the week 2 lecture, when we were discussing about the design equations related to the non-concentrating collectors, we described Qu in terms of Fr times APS minus UL TPM minus TA, if I am not wrong. Let's just quickly go through that section. Yeah, Qu is nothing but it's the useful amount of heat that is gained, and that is the heat which will be stored up. I mean, that is the heat that your liquid will take up and store it. That is nothing but it's expressed as AP times S minus UL TPM minus TA times Fr. Fr is what? Is the heat collector removal factor. So that is nothing but actual useful heat gain to the useful heat gain that would have occurred if the absorber plate was at the inlet fluid temperature. So these definitions are also available in the video lecture. So since here we can write that. Fr is nothing but Fr is the collector removal factor or heat removal factor. So this is nothing but it is the actual heat gain, I mean the useful heat that is gained to the heat that can be gained, gain if the absorber plate was at inlet fluid temperature. So if the absorber plate was at the inlet fluid temperature, then the amount of heat transfer that would have occurred will be more. So the actual heat gain will be more. So that is the reason we express it in term of this fraction. And if you see collector efficiency factor, that is nothing but F dash. So here if you see, we have expressed Fr in terms of F dash, that is your collector efficiency factor, and F dash is dependent upon a term called phi, which is nothing but called as the plate effectiveness. So these three equations, I mean these are very complicated, but yeah, so your Fr, that is the heat removal or collector removal factor, depend upon F dash, and that value of F dash, collector efficiency factor, depend upon phi. Phi is nothing but the plate effectiveness. So the collector efficiency factor is nothing but the actual useful heat gain to that of the heat gain if the absorber plate was at the local temperature Tf. So since it's the collector efficiency factor depends upon the actual useful heat gain, so the thermal conductivity of the plate will be affecting as a factor. So the collector efficiency factor doesn't depend upon thermal conductivity of the plate is false here, and this will be yeah, it will be false again. So this is again, it is something that is there only in your video lecture. Due to time constraint, we were also unable to discuss. So they are asking you to identify the type of absorber plate. You have this one, and they are asking you which type of absorber plate would be. So if you go through the week 2 video lecture, you will be having 4 different designs. So among them, one design is this. So let me just explain. So this is nothing but it is called as the tube in flat plate. So the tubes are actually placed within the flat plate. If you see this black line, this is nothing but it is actually the flat plate, and then the tubes are actually present between the flat plate. So this design, this type of absorber plate is called tube in flat plate. Suppose if you see the option B, it is called as a tube fastened to the lower surface of the plate. Then in that case, it will be somewhat like this. You assume this as a flat plate. Let me just you assume this as a flat plate, and then the tubes are present beneath this or at the bottom of this. So this design is called as tube fastened to the lower surface of the plate. So at the bottom of this plate, the absorber tubes are placed. So that is called as a tube fastened to the lower surface of the plate. And then the third one is called corrugated sheet on a flat plate. So over there, in this flat plate, there will be corrugated sheets that will be present, that will actually act as a channel for your fluid flow. So that one is this, and then the last one is the roll bond collector. What is a roll bond collector is, those will be the tubes only, but then the tubes has to be connected to the absorber plate, right? So if when there is a bond present between this tube and the flat plate, it is called as the roll bond collector. So roll bond collector is the absorber plate and the tubes are connected by using um, some adhesive, some kind of bond. So that is called as the roll bond collector. Just let me take this here. And tube fastened to the lower surface of the plate is tubes are present at the bottom of the plate, at the bottom of the absorber plate. So that is what is the difference. The difference is based on the location of the tube and the absorber plate. If the tube is if suppose if the tube is present at the upper surface, then it is called as the tube fastened to the upper surface of the plate. If it is at the bottom, then it is called as the lower surface. If it is present in the plate, then it is called tube in plate method. And depending upon the type of connection between the absorber plate and your tube, you can have something called as a roll bond collector. Over there, the tubes and the flat plate will be connected using a bond, some kind of adhesive. So this is about the solar energy, and most of the assignment problems, if you see between 1 to 5, we have solved majority of them in the live interaction session itself. So I would request you to actually go to those live interaction session as well as the PPTs to if in case if you have doubts on the assignment problems, then I would say it's better you actually visit that live interaction session video recording, or you can also look at the PPTs. We have solved majority of the problems on solar energy there. So I hope with that and this discussion, the solar energy is some sort of like come to an end. We have something on biomass energy system. So it's just only 3 questions, and I guess we it will be fine for us to finish this. So coming to biomass energy, the first question is, we discussed about the characterization of the biomass. Yeah. Hmm. Hmm. We have actually an expression for that. If yeah, the problem is this course is actually quite what do you say, equation intense. So monthly average, just let me look at once. Just give me some time, just for few minutes. So okay, I will just include that also, because I don't know which question actually you are talking about, and since all this, so I also need to look at the formula. So what I'll do is, it will be better that I will include those two, whatever you ask for. One is the peak power coefficient and another one is the solution for this monthly average that question, right? It's week 3 problem. Okay. Okay, yeah. So I'll just include those. Hmm. Okay. Week 3. Wait. Week 3, question number 4, right? Yeah. 1 minute. So, just a second. Can you see my screen? Actually, I'm scrolling through few of this thing. Do you mean this one? Because actually we have solved this, the week 3 assignment question. There were actually 2 questions that was there. Okay, anyway, I'll include that. I'll just check that once and then I'll include that, because we have to finish this biomass part now. Okay, I'll include that. So here we are asked to calculate, here there are actually, so if you see in the characterization of the biomass, we have totally 3 different type of densities. One is the true density, bulk density and apparent density. So here they are asking us with respect to the bulk volume. So since it's about the bulk volume, the answer is bulk density. But if it is in case of the true volume or the apparent volume, so apparent volume, over there you also include the pores that is present. So in that case, you have to calculate the apparent density, and true density is the total volume occupied by your biomass. So let me just mention that. So that is true density, and in case of this thing, it is the apparent volume, including the pores present in the biomass. So yeah, then this is the last question for today's session. We are actually burning the ethane fuel, and we are providing 24 kg of air per kg of fuel. If the theoretical requirement is 16 kg of air per kg of fuel, then what is the equivalence ratio? Equivalence ratio. So I hope we know the definition of the equivalence ratio. Equivalence ratio is defined as the theoretical air to fuel ratio to the air to fuel ratio required for that system. And here, to simplify our problem, the theoretical requirement and then the operating system requirement is given. So the theoretical one here is 16 kg of air per kg of fuel. And your operating system is 24, right? So 24 kg air per kg of fuel. So this one and the numerator and the denominator will get cancelled. So equivalence ratio is nothing but 16 by 24. So 0.67 or 0.66. So that will be C, option C. So with this, and I hope with all the other questions that we have solved in the previous this thing, I hope that now we would have got a much better clarity on all the three different aspects. And yeah, I will include that power coefficient and peak power coefficient, and then the week 3 problem question number 4 in the PPT itself, because actually we are running short of time. It's already 7:10 or 7:10. So I'll just include those two in the PPT before uploading those. And let me just stop presenting my screen. So do you have anything else that you would like to ask me? Like, if suppose I am unable to recollect now, then I can include that in PPT while uploading. Yeah, those two I'll include for sure. Okay, so in case if you don't have any more doubts, then let me just conclude the session, since it's our last week live interaction session. So let me just conclude that. I thank all the audience and the members who have joined this live interaction session for all the 12 weeks so far, including this extra live interaction session that was conducted today. Every week we have actually spent 2 hours on solving problems. I hope it would have been helpful for you. I thank the NPTEL team members and Professor Vaibhav Visham Gaut sir and Ananda Lakshmi ma'am for providing me this opportunity to interact with you all this Sunday afternoon from 5 p.m. to 7 p.m. for the last 2 to 3 months. I hope you would have learned and you would have enjoyed this course, and the live interaction session would have been helpful for you. So all the best for your exam, and thank you and bye. Yeah.